that I will start recording, and yeah, the people who are late can just watch the starting of the video. So I think it's good. How did it go with the exercises last week? Was it good for the first part? So the magnetics mechanics. Okay, I get this as a yes. And then we will start with the part magnetics and the heat PD. So first of all, we will discuss your homework, the second homework assignment. All the delivery dates are online in the Teach Center. So you got that. I think that you have to deliver this homework until the 26th of November. And what? 25th. And then we will discuss the homework in 2 weeks. So from today on, in 2 weeks, we will discuss the homework. You will get all the information in the today's course, or by the way, in the next week's course, and you will be able to answer all the questions. So far. Can you hear me well, and is it understandable?
Yes.
Okay, perfect. If you have any questions at any point during the lecture, just switch on your microphone and give it a go. So, excellent. What will the homework be about? It's very similar to the first homework you did. I think you had the discussion of the last homework last week, and this homework's discussion will be in 2 weeks. Okay, what's the homework about? Can you see my screen?
Yes.
Okay, perfect. So the first question on electromagnetics and heat coupling will be how do we come up with the magnetic field lines in longitudinal flux heating, and what's the direction of the induced current inside the sheet metal, and state the relevant equations. You will get to know what's longitudinal flux heating within a minute. So we will discuss it during the introduction for magnetic heat coupling, and you will be fine then. And most the other stuff you know from basics electrodynamics course, so I think it's very basic and you will be fine for this first question. The second question will be derive the weak formulation of the heat conduction equation stated here. So derive the weak formulation of this PDE. Assume that you have a domain. Probably I'm painting here some stuff. You have kind of a domain omega, and you have part of the domain is, you say you have a Neumann boundary, and the part of the domain you say you have a Dirichlet boundary. And just I have the weak formulation for this equation on this domain omega, and that's basically it. Everyone knows what to do for this example? Okay, good. The third question will be derive the Joule losses as a function of the magnetic vector potential A. I think everyone knows how to do it, and most of the stuff is in or all of this is in the slides. Question 4, derive the weak formulation of this equation, and introduce a multi-harmonic ansatz for the unknown. So for the unknown, it's the temperature T. The the unknown is the temperature. State the system of equations as we did it in the lecture for the curl-curl equations you see in the slides. I think we will got to that point in the next week's lecture to derive a multi-harmonic ansatz for a nonlinear partial differential equation. And yeah, that's actually the whole algorithmic is very straightforward. Yeah, so no big issue for that equation. That the fourth example, so you will be fine with that. And the fifth example is explain the skin effect derivation of the formula. So you should derive the formula, state the formula, and yeah, state what are the parameters the formula is depending on. So I know how is the skin effect changing with increasing forcing frequency or stuff like this. And what does it actually imply for a typical transformer? Okay, any questions on the questions? Okay, if it is not the case, we will start with the lecture. I will stop sharing the homework and I start sharing my screen. So you can now see my entire screen of the notebook. Is it correct? I guess so. Okay. So we are dealing with the second part of the time-dependent fields, which is for next year's then called multi-physical problems 2. The second part of the course will cover magnetics and heat coupling. Okay. We will first cover the heat equation, then we will derive a multi-harmonic ansatz for a nonlinear partial differential equation, the curl-curl equation of the eddy current problem, and then we will get into detail a little bit on the skin effect, and then I will show you an application which was published last year. Okay. Then the motivation for magnetics heat coupling is, or a lot of applications like surface hardening of gear wheels, stress relief, tempering, annealing. So very basic mechanical engineering stuff. Hardening, soldering, welding, induction furnace, and induction cooking plate. Any questions on that, how the processes are working? Do you have any idea how surface hardening works? Okay. Maybe Alexander Siegel could explain what is happening when we do surface hardening.
I guess I tried to explain, but I just wanted to say no, I don't know it. So maybe you can explain.
Okay. I usually surface hardening is usually done when you are having steel material. So, for instance, you have a gearing rod, like it's just a round bulk material, which is usually used for shafts in gearing systems. Then you cover this shaft with induction windings, and then you heat up the stuff, so the material in the outer region of the shaft, and then you just put the material in a cold pot like water and or oil, and then due to the properties of the steel the surface where you have the sharpest drop in temperature over time is hardened. So this is actually used for hardening the surfaces of the shafts. You somehow got an idea?
Yes.
Yes.
Okay. Perfect. And yeah, all the other methods like welding, they are all processes where you need somehow a heat source, and in the most of the applications use the current in some copper windings for supplying energy to heating up the material. That's usually how it works. Any one of you knows what's the formula? Probably.
Penetration depth of the eddy currents.
Okay. In which course do you hear that? Because that I get some impression of how your background is. Because I think my background is mechanical engineering, and I think you all know how eddy currents behave and what it is about. Do you learn it in electrodynamics?
Actually, we have an advanced course called Theory of Electrical Engineering, where
Okay.
you learn the basics of potential formulations and eddy currents, and then also some basics of finite elements and then boundary element problems. And I think pretty much at the end, you have a deeper investigation of time-dependent processes, and of course they learn about penetration depth and then skin effect and other of those effects.
Okay, perfect. So I think you're, as all of you had this course, I think you're well suited for the lecture, and probably I just can explain you a little bit about the heat equation, but the rest of the methods you all already know, and also the background theory. So probably at some point I will probably select one of you, like Tobias, to explain a little bit details what we are going to hear. Okay, perfect. So this is the penetration depth, and we will now go on with the lecture. How it usually works. Can any one of you explain what is longitudinal flux heating? Okay, then I will just start what is longitudinal flux heating, and maybe one of you then tell the others what's transversal flux heating. So in the longitudinal flux heating process, usually what we aim for, we have here a sheet material, which is the gray sheet. It is usually moving in one direction. Let's say we have a sheet moving in this direction at the velocity v, and during the movement, people or workers usually would like to do something with the sheet material. There are a variety of different processes but one of them is longitudinal flux heating. You have some copper windings here, and you have some current flowing or being in the copper windings, and it induces magnetic field lines, and these magnetic field lines would like to penetrate the sheet material, and the sheet material reacts, counter-reacts in induced eddy currents here, and these eddy currents would like to kind of shield the material from the penetration. Was this kind of understandable? I think most of you get the explanation a little bit better than I, but would some of you try to how transversal flux heating works to explain to the others? I would just select one. I think Tobias Lava knows it, how transversal flux heating works.
I'll try to explain at least. I'll explain what I understood.
Okay.
In the longitudinal case, you have the currents as you see at the zoom on the right side, that the eddy currents are flowing in the plane of the cross section of the sheet, which means that I think the heat flux density points into the V direction, as you have, for example, here the currents. You have higher currents flowing around the copper coils than, for example, at the beginning or at the end of the sheet. And in the transversal case, you just have the eddy currents flowing in the plane, just in the big plane, so the plane where the normal vector points up or down. Just such Stefan drawing here. And of course that corresponds to a different heating behavior. But the actual heating process I cannot explain in detail. I think I didn't get that completely.
Okay, excellent. The details on the heating process we will get at the end of the section. So on this second part of the multiphysics. So the whole publication or application example is considering this transversal flux heating process. So I think we will see some heating up charts and stuff like that.
I have a short question.
Yeah.
So the difference between the longitudinal and the transversal flux heating is the direction of the eddy currents and how the eddy currents are flowing?
Yes.
Okay.
And this gives some, nicer properties for the one and some other advantages for the other.
Okay, but we will talk about this later.
I'm not 100% sure, but for very specific details, you can always ask Klaus. He is the guy doing all this, magnetic heat coupling simulations.
Okay, thank you.
But we will see some of the ideas and the background at the end of the whole section, magnetics and heat, when we talk about the applications. Okay, so what's the physical process in total? So we have a electromagnetic field that induces eddy currents in the steel material. Of course, we need an alternating field because we would like to have induced some induction here. Then we get the eddy currents here. So here we see the eddy currents, And then with that, we with the alternating eddy currents, we produce heat in terms of the Joule losses inside the sheet material. So the Joule losses are stated here. One of the questions you will have to answer is how do we come up with the Joule losses being like a function of the vector potential? It's more or less written here. So that's actually no big deal for you. And yeah. The takeaway message for this slide here is that we need an alternating magnetic field, and electric conduction is important to actually get this upheating. Yep.
The Joule losses is also a vector.
The Joule losses should not be a vector. That's a power density, as I know, but maybe I'm wrong. You have here an inner product.
It's an inner product. I see. Yeah, okay.
Yeah, and this square is just more or less doing. Yeah, sorry.
I see.
My
Yeah,
writing
okay.
is a little bit sloppy here. So that you have the inner product of the vector potential.
I see. Thank you.
This means the square here. So let's just write it like this. Okay. Everyone got the connection between what's happening in the application to a more abstract way. What are the basics?
Yeah.
Okay, perfect. Then we go on. We go more deeply into the heat conduction equation. The classical heat diffusion equation can be derived by kind of thinking of a control volume. Probably before we start with the heat conduction equation, did any one of you have thermodynamics or any fluid dynamics, or have you ever heard of a control volume?
No.
No, also from my side.
Okay. So probably we start with the control volume. Have you any idea what we could mean by that? Probably not. A control volume is just a thermodynamical representation of a specific volume. In continuum mechanics, just think about it. You have a domain. So in finite element context, you have a domain like omega, and in thermodynamics, we just say to this domain control volume, and to the control volume something happens. Like the control volume has a thermodynamic state, and when this control volume has a thermodynamic state, we can also apply the rules of thermodynamics and derive the kind of the first law of thermodynamics, like the conservation of energy and stuff like this. Any one of you heard conservation of energy?
Yes.
Okay.
At least in an electrodynamic sense.
Okay, perfect. And I will start to explain it to you in a more general kind of sense or setting. So you have here the energy of as a state of this is the change of the energy of the total energy U, of the fluid inside or the material inside the control volume omega is equal to the applied heat fluxes. So we just point here an arrow down there. We have some heat sources generating a heat flux onto this control volume. Imagine a very practical thing, also in electrodynamics, like the sunlight is also some heat flux, and the sun kind of heats up a material which is lying on the ground. Okay, here we have some heat sources or heat contributions on the control volume, and we have some power acting on this control volume. Do you have any imagination what this power could be?
Forces from outside, deformations or something like this?
Yes, that's a good example. Deformation. Any other idea?
Maybe in a combustion engine, this is the mechanical power we gain from the combustion of the fuel air mixture.
Yes. Any other contributions? Probably Lucas, Daniel.
Sorry, I don't know any example.
Yeah, probably you can use the Joule losses.
Okay.
Michael, do you have any idea? Okay, so yeah, we have some power which can contribute to the control volume and changes the inner energy of the material. And if we assume an incompressible media and using the caloric law, okay. Does anyone know what's an incompressible media or medium?
No, I don't know. I don't know how the others.
Okay, incompressible means that you have a medium that does not change its density along a particle streamline, which is very abstract. It simply means that you have, so in a more natural way, it means that the divergence of the velocity is 0. And this also means that in a very simplified way, it means that the density is constant. So you have a constant density in the material, more or less. And so for a fluid, you have a constant density. And anyone knows what's the caloric law? Also probably not. The caloric law is that the specific inner energy is equal, like a coefficient times the temperature. So this means that the internal state of energy from a usual medium just depends on the temperature state. So just on the temperature of the medium and a constant.
If it's uncompressible.
Yeah, if it's incompressible, then this more or less holds. So for the whole setup here, this is true. In the first equation, we need the incompressibility, because here we have the density and we move the density here in front, and the caloric law we use for the second equation. So probably a little, sorry. The two assumptions walk in. The first one walks in here, and the second assumption walks in here. That's how we derive the equations for the first part of the conservation of energy, or in the following for the heat conduction equation. Okay, this means that du dt is proportional to the temperature, the time derivative of temperature, and now we would like to model the source terms, like the heat flux which is imposed. There we use Fourier's law. Anyone knows what's the law about? Probably we try again. Michael, do you know what's Fourier's law?
I think it's something with the temperature and how it depends with the heat flux.
Okay, yeah, this is true. So Fourier's law is a general, like, think we have here a surface. This surface is called the omega. Probably modulo direction. We have here heat flux, and this heat flux is equal. I'm not sure about the sign here, but depends on a heat flux coefficient and the gradient of the temperature. Now, this model is Fourier's law. So the heat flux depends on the temperature gradient. And for different materials, you have here different lambda parameters. And usually what people do when they put on their houses all different materials shielding the house from getting the heat out or getting heat in, they are just modifying this lambda parameter. Okay. So this lambda parameter is more or less the heat insulation. And then for the power dissipation here, or the power generation, we assume that we have the Joule losses here, and the Joule losses are a function, or are generated inside the material and have a density, and they are generated as volume sources. And we can model the Joule's losses here by this little volumetric heat sources. Okay. Everyone got the derivations and the connections of the different terms of the classical heat diffusion equations?
Q is the heat flux, right?
Exactly.
Lowercase
Q is
q.
the heat flux, and P is the power.
Okay. What's the unit of the heat flux? Temperature? Yeah.
Wow.
Okay.
It must be the same same as for a power.
I see.
The power is somehow
What?
watt
Hmm.
a prob. Yeah, hopefully I'm right. And the same is for Q and du dt. Yeah. So the energy is typical somehow joule, and yeah, the sources are then watts. Yeah. Any other question? So if it is not the case, we just move on with the course. Okay. So we did a lot of manipulations here on this slide, and then we derived the heat conduction equation here. Okay, does this make sense for every one of you? Or should I describe the missing parts in between?
For me, it looks okay.
Okay, perfect. Yeah, then there is another issue. So this heat conduction equation up there is derived for a fixed volume, and we have no moving control volume. If we have a moving control volume, like here, the sheet is moving, then we would have to use here Reynolds transportation theorem. So I just draw here in an arrow that we get the connection to the other slide. We would have to use also, in addition to the incompressible media, we would have to use here the assumption that we know Reynolds transportation theorem, and then we arrive at this equation. So we here started the arrow or the line from the other slide, and then we would end up here. Anyone knows why? So the Reynolds transportation theorem uses or gives an additional term, which is the one is the change in time. So the real temporal change of the temperature itself, and the other term makes convection. So how a temperature gradient convects with the loss velocity. Does this make sense for everyone? Yeah, probably it's a little bit difficult to get to the equation, because I assume that almost nobody of you knows what's Reynolds transport theorem about, but it is frequently used when you are considering moving media or moving control volumes, and then you always get a term which is depending just on the partial time derivative, so it really tracks the change with respect to the time, and the quantity always comes up with a convective part that you can monitor also the change with respect to the fluid velocity. is it okay for everyone just leaving this equation here like it is? Or would you like to have some further explanation on it?
I just have one question. Why is lambda, so in the upper equation it's a function of T, of the temperature, and now not anymore?
Okay, it's just for simplicity here not
Okay.
written, but here it would also be a function of T.
Okay, so this is the same term, like in the
Yeah,
upper
that's
equation.
totally
Okay.
the same term.
Okay.
So typically the C underscore P and the lambda are functions depending on T. So these are not really constants, but in a wide range they are constant.
I see. Thank you.
Any other questions on the equation? Okay, then okay, then we already get to the parameters, the material parameters on the next slide. But before I probably discuss what's the equation about. So we really have here that temperature field, which is this heat stuff, which we were talking. So that's the part where all the temperature dependency is modeled, and when we apply different heat sources, here we have a heat source, for instance, heat source due to the eddy current, the equation on the left side, or the left side of the equation, models all the heats and how they contribute to the temperature, and the right side is, so in the sense, the forcing, like if you apply eddy currents and induce the Joule losses and stuff like this, then we will get some sources that increase or decrease heat, but yeah, usually they increase the temperature of the material. Read the equation in a more physical way. Okay, and then we now go on in terms of how the parameters are depending on the temperature. We have here some nice graphs that the material parameters, like the thermal conductivity, which is the lambda, is somehow, okay, the lambda is here, which is a function of the temperature, but can be approximated by a linear behavior. And also the heat capacity, the heat capacity is the Cp. Probably to note, don't be confused, there is a Cp and a Cv. The Cp is the heat capacity at constant pressure. So the thermodynamic state is isobaric, and the heat capacity C under subscript V is for barotropic, so for not changing volumina, and these are a little bit different, but here we use the Cp. Okay. And the material parameters are weakly nonlinear in the temperature, as we see here, and yeah, that's basically it. For the typical boundary conditions we are using is and we also need them in one of the examples, is a Dirichlet boundary condition, that we just fix the temperature on the boundary of our volume, or we have a Neumann boundary condition, which is a prescribed flux, and the flux in terms of a heat flux, which is modeling this boundary condition in terms of the Neumann boundary, and then we have some combined boundary conditions like a Robin boundary condition, which is a convective heat transfer. And there are also possibly nonlinear boundary conditions, like if you are modeling some radiation, so heat radiation, then typical the radiation is proportional to the temperature to the power of some exponent, like to the power of 4 or a different exponent, and then we also have some nonlinear boundary conditions. Yeah, but we don't consider any nonlinear boundary conditions in this course. Is it good for everyone to leave the boundary conditions like they are?
Yes.
Okay, perfect. So these are the boundary conditions we usually have in our PD setting. We use standard Lagrangian novel finite elements. We have term here. Yeah, it can lead to instabilities of the scheme. Therefore, it's more preferable to use an implicit time-stepping scheme, and it results in a non-symmetric system matrix, which is also not so nice in terms of the solution strategies. Typically we can discretize at the time by a simple time stepping, like the trapezoidal rule. I think you had it learned in magnetomechanics. Is this right? I'm not 100% sure if Manfred covered it.
He slightly covered it, but not very detailed.
Yeah, it's not so important, but usually time discretization. There are a bunch of methods how you can do it. It is also possible to discretize time with finite elements. You can do it as you like. Okay. Any questions so far on this slide? Probably not. Then we go on with the coupling terms and how we plug in the Joule losses. Okay, excellent. Just going back once more. So we have here the reminder, the heat conduction equation, and on the right side we couple in the Joule losses. So the Joule losses are the right-hand side of the equation. And for the non-moving case, the Joule losses in terms of the vector potential are simply stated here. And in the moving case, they are going to be a little bit different. Will be more or less straightforward for you guys as you had electrodynamics and this special advanced course in what was the name of the advanced course once more?
It's a theory of electrical engineering, and it's, I think, held still by Professor Biro. And I think in next summer term or next winter term it will be held by Professor Kaltenbacher, or at least in the future. I think Professor Kaltenbacher will overtake it.
Okay. Yeah, and I think you will also learn how to probably consider And then to go on or speak a little bit about different effects. So we have on the one side the electric conductivity, on the other side it depends somehow on the temperature, and typically we have an excitation frequency of a coil in some of the kilohertz range, and usually the heating up takes very long. The heating up takes some seconds. If you have a kind of a super fast egg boiler, it's it's probably heating up the water within some 1 or 2 seconds, but usually it takes time, and the frequency or the loading of the coils is usually done in a much higher cyclic way, and there we have some very different scale from the excitation range to the actual application in terms of the physical effect, which means if we have an oscillation of the current like this, the temperature is probably changing very slow. And the idea facing this challenge is that we solve the electromagnetic field in the frequency domain and then couple the effective power of the electromagnetic field into the heat equation. Everyone understood the idea?
So stationary solution of in the frequency domain.
Yes. So
Okay.
we apply, for instance, some sinusoidal excitation and say, okay, where is this sinusoidal excitation then going to be at a stationary point? So we are actually searching for a limit cycle. So if you have the phase plane, and if something is kind of moving in the phase plane like this, it should be a closed loop at some point. Good. Okay, so we are searching for periodic solutions. And that's the idea of the coupling. You can also do the coupling in time domain, but in time domain it will be kind of exhausting doing such a computation, because if you do a computation and you have different time scales in your physical simulation, then you would at some point have to consider somehow the faster time scales. So your discretization will depend on this 5 to 10 kilohertz. And you should calculate at least so long until the temperature field gets stationary. So this means you probably have to calculate a lot of cycles of the current. If we say here we have the current, and here we have the temperature, and we would like to discretize this, then we need for each period some discretization points here, and this is very exhausting in the temperature range. So we would have the very bad compromise in the time resolved scheme, where we need to resolve this 5 kilohertz, but we also have to compute a lot of seconds until to get a stationary temperature. And the idea is then to go for the electromagnetics stuff where we have these high oscillating frequencies into the frequency domain, and yeah, there we see how to apply the multi-harmonic ansatz for the actual computations. Okay, any questions so far? Okay, I take this as a note that we have no questions and we just go on. Okay, we had the idea that we now apply a harmonic ansatz on the curl-curl equation.
Was it me or was your connection bad?
Okay, I think it could be that my connection was bad. Do you have any questions on the last slides? I think no. We will just start with the multi-harmonic ansatz. We are interested in a quasi-steady state solution of the eddy current problem. Every one of you has an idea where the equation comes from.
I think yes, those equations, or at least this equation, was already covered in the previous lectures.
Okay, perfect. Thanks, Manfred. Okay, this is the equation we are now discussing, intensively for the next 10 slides. And always have in mind, we are focused on this equation, and if I say curl-curl equation, then it's this equation, it's the eddy current problem, where we have on the right side the impressed current and the derivative of the time derivative of the vector potential. We assume that the vector potential is a periodic steady state solution. As I said before, in the phase plane, it should give a closed circle. It doesn't really matter how it lies in this plane, but it should be just closed. So as it's stated here, so the last point of the vector potential should be the first point, and it should all go in circles and stuff like this. And it should, satisfy this equation here, the eddy current problem, and that's basically it. To satisfy the periodic stuff, we can do an Fourier series expansion for the magnetic vector potential. We also do a similar ansatz for the material parameter here. So we also do an Fourier series expansion, but with a different order here. Usually we don't cover as much harmonics for the magnetic relativity. Any questions on the Fourier series expansion? I think it's very straightforward, and you all heard it in the classical math course. I think there's no big deal here. You will have to do something similar as we do it here for this equation here. Okay, so for the fourth example, you're simply doing the stuff we are now discussing for the multi-harmonic ansatz. Okay, Yeah, step number 1. We'll just repeat it once. We would like to have a periodic state, and we would like that our solution satisfies the eddy current problem. To ensure periodicity, we do a Fourier series expansion, and we also do a Fourier series expansion for the magnetic relativity. Then we plug the whole stuff into the equations. The equation up here. And yeah, that's basically it. We have now this very confusing equation. And we do then a multiplication by this exponential factor, and we integrate over one period. Okay, so far nothing difficult happened. Any questions? Is this understandable for everyone? Yeah, probably Tobias.
Yeah, from my side, it seems everything seems clear so far.
Okay.
Yeah.
Okay, it was just no big deal. I probably repeat it once. We have here the magnetic relativity. We have here the vector potential, and we also have a vector potential here. We now insert the ansatz here for the magnetic relativity. We also insert the ansatz for the vector potential, and here also the ansatz for the vector potential, and we also executed the time derivative, and we inserted the ansatz for the current, so for the impressed current. Then we took this equation, multiplied it by this factor, and integrated over the time period. Okay, perfect. So the final step was integrating over one time period. And then we can exploit some properties. These are the properties we're using, and if we use that properties there, we then get, oops, it seems that the system of equation is here out of out of the slides. Okay, good. Yeah, no worries. Okay, we have here we then obtain a matrix of the magnetic relativity where we have contributions up to the order m. So before I said we have here the order m. We have contributions up to the order m, and here on the rest of the matrix block are zeros. So I'm aiming to write this down here. Okay, so that's the first block of the equation, and that's the curl block. So here we have a lot of curl equations that are connected, and the second matrix, which you are not seeing here, will look like this. We have here this matrix, just the entries on the diagonal, and we have here the vector being these quantities just here, and this is equal to the impressed current. And the impressed current should now be I will give you the details within the next lecture here. Or upload a slide where the whole system of equation is stated. Okay, this seems we have first here the block, the curl block, then we have the time derivative block, and on the right hand side we have the impressed currents, which are simply connected to the impressed current here. Okay, this is how it works. Yeah, I'm sorry that we don't see the full matrix, but here on the next slide, it's going to get a little bit precise. The curl block in total is a system of stiffness matrices. So here again, 0 entries. Here we just have the diagonal connected to the time derivative. So all the side matrices are 0, and here we have the unknowns. These unknowns are vectors. These coefficients are system matrices itself. So K is a matrix, M is a matrix, and the A is a vector. And Q is also a forcing vector. And this means that we force with our forcing at a specific harmonic. So the forcing is at the first harmonic. We force the first harmonic, but due to the non-linearity of the relativity, we get additional contributions at the higher harmonics. Is this clear for everyone? Did you get the message? Okay. Was it understandable for you, Lucas?
Yes, I think everything was clear.
Okay, good. So to get back on the derivation of the weak formulation. So you should state the system of equations as we did for the curl equation. It means I would like to see you how to derive this system of equations. Like that you have all the blocks aligned as we have it on this slide. But this is actually the outcome of the fourth example.
So this Q is now our J?
Yeah, it's yeah. Sorry for the notation. Yeah, the Q is the J. I will update the slides and put the correct slides online.
Thank you.
So this should be J. Okay. And yeah, the stuff you are not seeing, yeah, is not displayed here. Actually corresponds just to the system of equations here. Okay. Then we go on. So the scheme of how to compute the stuff is that we have an initial idea of what our magnetic relativity is. So we choose a linear contribution of the relativity and solve the linear system in the frequency domain. When we solve the linear system in the frequency domain, we get a first solution. This solution, we go into back into time domain, do an inverse Fourier transform, and then get the magnetic vector potential in the time domain. Then we can go into the BH curve, the nonlinear, and evaluate the magnetic relativity for the actual magnetic relativity, which will not be the same as the relativity at the zero stage. When we have this relativity there, then we can apply the Fourier transformation for the magnetic relativity. We obtain the coefficients of the magnetic relativity. Then with these coefficients, we can solve our multi-harmonic system of equation. So this, what we are solving here, is actually this system here, and obtain a new iteration of the magnetic vector potential, then do again a back Fourier transformation, and then have the magnetic vector potential again in the time domain. We do an update with respect to the BH curve, and do this cycle until we converge or do not converge. It depends on the regularity and how the slopes of the magnetic relativity are, at the monotony of the magnetic relativity. But usually in a good setting, we converge and all is good, and we have the final solution. Is this algorithm or computational scheme clear? How it works?
Yes.
Okay. Good.
I have one question.
Yes.
What would it be if we would assume a linear assumption for the relativity?
So that the relativity is linear.
Yes, it is linear.
Okay. If the relativity is linear, blah blah blah. If the relativity is linear, this
okay. So
would not be here. Then we have a linear system. If the relativity is linear, then we do a Fourier expansion just with the first harmonic. Then everything is linear. We get a system of equation just in the first harmonic, and that's it. So probably the system then looks like this. We have the K minus J omega M then we have here the vector potential, and is equal to the impressed current. Then we just solve this equation and that's it. So if everything is linear, in the linear case, we just solve this equation. We don't need any iterations or stuff like this. It's good for you?
Yes, okay.
Okay, yeah, and that's basically it. So in the linear case, very straightforward. No big deal. Okay. Then we go to one example. So for instance, we have here a coil. So here the red thing is a coil. So coil here around a iron core. The green stuff is iron. Yeah. Usually my colleagues from mechanical engineering will hate me because iron is always blue, but here it's green. We do a transient simulation and we have an excitation or an impressed current. This here is now our JI, the impressed current of amplitude of 80 amperes and 10 hertz. It is impressed and we have 250 turns of our coil windings, and we do a time discretization of 2 milliseconds. And the idea of this example is that we get a benchmark. So the transient simulation, everyone knows what's a transient simulation. Just means that we solve in the time domain. So just doing a time stepping scheme and discretize the time. The idea of this example is to get a benchmark for our multi-harmonic ansatz. And the result is the following. That we get a magnetic flux density inside the iron core, which is shaped like this, and it's somehow non-linear. Everyone sees the non-linearity.
Yeah.
So it looks a little bit non-linear here, and also a little bit here. Could be some superposition of different sinusoidal components. Okay. The first harmonic, so the excitation harmonic, contributes the most, and then we have some higher harmonics, which also contribute a little bit to the solution. Okay, that's it. Any questions on that transient simulation? I think most of you already did some calculations in CFS++ or OpenCFS. So I think it's all clear for you how to do such a simulation, and we also will do some stuff on this magnetic heat, and it will be how to do the simulations. Okay, then we will proceed. Usually we have a computation curve as we have it here, and there is also a hysteresis, but at this point we don't consider any hysteresis. The hysteresis topic will be covered in the special sessions at the end of the course, and we just consider nonlinear relativity as we illustrate here, and it should be symmetric about the origin. Okay. Based on this, we can exploit some properties of the Fourier series, and with these properties we can reduce the complexity of the system and drop some higher harmonics which are not contributing at all in terms of the heat conduction. And yeah, that's basically the consideration of the last two slides, and this is more or less how it works. Any comments on that slide and the last slide? They are very specific, and if you encounter any, or you are in the position that you have to define a multi-harmonic scheme for any physical field, then you probably should look up at these slides and consider them in terms of computation, increase the computational performance, because it reduces the equations by a factor of 2, and this enhances the solution in terms of speed. Any questions on that? I think not. So then we will go on with the eddy currents and the skin effect. Any one of you would like to explain the eddy currents? Yeah, probably Lucas. Would you like to give it a try?
Yes, I can try.
Yeah.
Eddy currents occur because of Faraday's law, so that the rotation of the electric field is equal to the time derivative of the magnetic field. So if you have a varying magnetic field, then an electric field is induced, and this electric field contributes to the eddy current.
Okay. Perfect. Okay, this means so just in terms of this, then the eddy currents are produced or somehow induced in the winding, or in the bulk where the current is where the current is flowing, and they kind of shield, or yeah, I'm sorry, I lost the word. So they are, yeah, sorry, I lost the connection.
Sorry?
Ja, sorry, ich habe gerade meinen roten Faden verloren. Ja. Yeah, I lost the English words. So in a thin wire, or in a alternating voltage driven coil, or thick bulk material, there are a lot of or the alternating current, and as you said, for regarding Faraday's law, we have eddy currents that are induced, and they displace the current inside the material towards the skin of the wire, and then we have the current distribution. So the homogeneous current distribution is distributed inhomogeneously towards the surface of the conductor, and this is then the skin effect. So the typical current is then flowing in the skin of the conductor. So sorry for the confusion. Was this somehow understandable now? That the skin effect is that the current of a thick conductor, when the current is alternating, then it's kind of distributed to the surface.
Yes.
Okay. I think most of you are experts at this, so I think it's mostly clear for every one of you, and we will just call it a day, and we will cover the eddy currents and the skin effects next week again. Probably who of you or all of you participated in theory of electrical engineering?
I did.
I did too.
Yes, I did too.
Okay, there's probably one person left, which
Long time ago.
okay, long time ago. Probably before we close the session, I would like to go over the slides and very briefly and ask you what type of theory you already know, that we probably can cover it next week in a faster fashion. So the eddy currents and the skin effects, the basic equations are probably known to everyone. I guess so. And also how to derive the penetration depth. Is it basically clear for everyone?
I mean, I know the final formula at the bottom
Okay.
of the slide, but I never did the exact derivation.
Okay, then we do the derivation, and also how to model the stuff. Yeah. Okay, then we'll cover it next week.
Yes,
Okay,
please.
excellent. Perfect. So once more, the takeaway message for today, you all know what's the heat conduction equation, you will know what's the multi-harmonic ansatz, and you know eddy currents and the skin effect, and we will start next week by considering this equation here, the curl problem of the flux, and then derive the penetration depth next week. Okay, then call it a day. I call it a day, and we will see us within a minute in the exercise. Goodbye.
Bye.